Right, so in this lecture I would like to talk a little bit about the contradictions between writing software in such a way that is easy to debug versus software that is actually fast. So I entitled this as Debug versus Optimized Builds, and let me motivate this whole thing as follows. So in scientific computing, oftentimes, of course, we live in a tough spot. We have computations that we know are going to be long and expensive. So if you want to simulate, let's say, the flow of air around an airfoil, you cannot do this in seconds. We know that it's going to take hours or maybe days to solve these sort of problems. So as a consequence, we very much care about performance. We know that we need to write our software in such a way that that is on our mind. We can't afford to have software that is really slow. On the other hand, there's of course also an expense to developing software, not just to running it. And I think it is worth reminding ourselves of a fact that we sometimes forget, namely that the most expensive thing that we have is our own work time. This is certainly true in a country like the United States, where computers do not cost very much compared to salaries. Even for a graduate student, buying expensive computers is a relatively small fraction of the overall cost of a graduate student, or let's say the salary, the health insurance, and so on and so forth. This is certainly different in other parts of the world, but even there, it is definitely true that your own time is the one thing that you cannot buy. Even for no amount of money, at the end of your time as a graduate student, for example, you have to have your program done. Or if you are a postdoc or a faculty, you have to write your papers. You cannot afford to spend as much time as you want on software. You have to get it done. So certainly the speed with which we can develop software, the speed with which we can debug our own problems in our software is a really important consideration. And it must be a goal of ours also to make it simpler to develop codes, right? This is one of the two important considerations other than making it fast. And in my view, I think it is actually the more important one. That doesn't mean that we, of course, should lose sight of performance. Of course, we should know where our codes are slow, but we need to address the issue of being able to develop our codes in an efficient manner. So it turns out that as a general rule, it is almost impossible to achieve both of these at the same time. We can get there partway, but I think we're very much aware of the fact that you cannot have both. If all you cared about, for example, is the speed with which you would develop codes, then you would use scripting languages, let's say Python, for example, that are much easier to code, that don't need, let's say, long compile cycles, for example, that have, let's say, more help for programmers, that have bigger standard libraries than C++ has, for example. But at the same time, of course, the executables that come out of it are vastly slower in many cases. Maybe not by orders of magnitude, but certainly by appreciable factors. On the other hand, if all you cared about is performance, then you would write your code in assembler or just barely better in Fortran, for example. Say Fortran 77. Fortran standards after this are much more modern programming languages. But so this is sort of the setting of all of this, that we need to find the balance between being able to run our codes in an efficient manner and being able to write our codes in an efficient manner. And so what I would like to talk about is essentially two strategies that we have developed as part of deal.II that others, of course, in software design have developed as well. So the first one is dimension-independent programming. I think this is probably the most unique part about deal.II. That is based on the observation, of course, that 3D computations are far more expensive than in 2D, and as a consequence, they're very difficult to debug, right? If a bug only happens after an hour of runtime, it's very difficult to find the bug because the turnaround time is just so incredibly long. You can't just, edit it, fix the bug, run the program, verify that it works. You will have to wait for an hour, and if that was not the correct fix, your program might still crash or still give the wrong answers. And so debugging problems in 3D is just very difficult, very awkward. Whereas in 2D, it's much cheaper. Computations run much faster. It's they need less memory. They're more interactive. You don't need as many processors if you run in parallel, for example. So everything is simpler in 2D. And you have seen how we did this in step 4, and then in step 5 and step 6, how we implement our programs in a way that is dimension independent by making everything a template on the dimension, because then we can develop the code only once. And if we know that it runs in 2D, we can be reasonably certain that it will run correctly in 3D as well. So we develop and we debug in 2D, and then the code that has been debugged can be run in 3D for our production runs. So this is one way how in deal.II we address this contradiction between performance and debuggability or developability, the ability to develop code. The second approach is something that we call debug versus optimized builds. So in deal.II, we have a lot of places where functions check the input arguments. So I showed you before what happens, for example, when you try to access the 12th element of a vector of length 10, for example, that the program is aborted, and that there's a place in deal.II that just verifies that the indices that you access are valid, and if not, just terminates the program. So there are a lot of places in deal.II where we check the validity of input arguments. There's also places where we verify the consistency of an internal state, and I'm going to show you examples of this later on. If these conditions are not verified, we abort the program, and then that makes it that much easier for you to find the problem in a debugger. You remember the lecture that I gave on Eclipse, where I showed you what happens in that case and what happens if you run this in a debugger. Eclipse essentially stops the program in the place where we aborted it, and then you can go up and down the call chain, and you can see where you called this from. You can look at the local variables and their values and so on and so forth. So typically when you abort a program because one of these conditions is not satisfied, the solution to the problem is fairly obvious. Certainly much easier to find and much easier to fix than if the program just produced the wrong answer, and you would have to find out why that is so. So the technical implementation of these sort of conditions that we want to verify is through something that we call assertions, and I'm going to give you examples of this in the next few slides. deal.II, as of early 2013, so right now when I videotape these lectures, has on the order of 8,000 such assertions. So it's a very, very large numbers of places where we check code, where we check the validity of input variables, where we make sure that the output of a function is correct, and so on and so forth. And of course, what you will find is that while you develop your programs, you hit many of these assertions. It happens all the time. The message for this is essentially these are all bugs that you had in your code. And so the more you hit, the more of these assertions you hit, the better it is for you, because it means that this is a problem that's easy to fix. So that's our goal when we write these assertions, that we have as good a coverage as possible of potential problems, of places where people try to give an invalid argument to a function, that we want to catch these sort of cases. So I would like to classify these assertions that we have into 3 different categories, namely preconditions, postconditions, and internal conditions. So a precondition typically is a function gets an argument, and it wants to verify that the input argument or a group of input arguments collectively is useful in some sense. So let's say it satisfies the constraints under which this function can usefully produce any sort of information. We call this preconditions because this is something that we can verify at the very top of a function. And as a matter of fact, in some programming languages, there's even before the function starts, there would be a block of preconditions. These are just essentially conditionals, let's say Boolean expressions that have to be verified. So it doesn't only have to be a single argument that's involved in this. It could be, for example, that a combination, the product of 2 input arguments must be greater than 0 or something like this. All of these sort of things runs under the name of preconditions. Oftentimes what you will find in deal.II is that these preconditions are recorded in the documentation of a function. So the documentation will say this index has to be between 0 and the number of elements of this vector. That would be a documentation of a precondition. In some cases, newer versions of the documentation tool that we use have a tag. So in some of the newer pieces of the documentation, it is actually marked as a precondition. It turns out that from, let's say, an empirical viewpoint, the vast majority of bugs that we put into our programs, everyone who programs has bugs in their code. The vast majority of these is that we violate preconditions. It's not typically logical errors, but it is that we call a function where we accidentally reverse two arguments, or we try to access an element of a vector that we think has size 15 and we access element 12, but in reality the vector has only 10 elements. And there's two possibilities why this is wrong. Either because the vector really should have 10 elements and we access an element that's not valid, or because the vector has been resized to the wrong size. For example, we might have resized it to the number of cells and not to the number of degrees of freedom in a mesh. In either case, having the program being aborted if we access these elements is an easy way for us to find that there is a bug in the code. And so it turns out that I would say between 90 and 95% of the bugs that you will write in your programs are violations of these preconditions. So the fact that most of the deal.II functions check the validity of input arguments makes it a lot easier to find these sort of bugs. So I would like to show you an example of this. So I'm coming back to this accessing an element of a vector of length n. So the precondition in this case would be, if you adopt the C indexing notation that you start at 0, the precondition would be that this index I of the element that we access is greater or equal than 0 and is less than n. Okay? So a typical implementation would look like this. So we have a class vector and it stores the data as some block of memory, and we store it as a pointer to the first element of this memory, and it has a variable that denotes the size of this vector. And then we would have an operator square brackets, for example, that accesses the ith element of this vector. And so a typical implementation would utilize this thing that is called assert. That's a macro defined in the C programming language, and that verifies that I is less than size. Size is the size of the vector. I must be less than this, so this corresponds to this right inequality here. I don't check the left inequality that I is greater than or equal than 0 because I have made I of data type unsigned int. Oftentimes you find that other programmers just use integer for everything. In deal.II, we're very consistent with using unsigned int for things that really cannot possibly be negative. So the index of a vector element cannot possibly be negative, so it should be an unsigned integer. And of course, unsigned integers by default are always greater or equal than 0, so we do not need to check the left inequality here. All that's required for us is to check the right inequality. So what assert does is, if the condition is not true, it aborts the program. That's exactly what we want. In that case, the program would abort. If you run it in the debugger would stop at exactly this location. You could go back in the call stack and you would know exactly where it happened and why it happened. On the other hand, if the condition is true, so if I is in fact less than size, then it returns the ith data element. That's of course what we wanted from this function. So this is what we do this is how you would write this if this was a standard C or C++ implementation. In deal.II, we have a slight twist to this. So we have our own macro that is not called assert with a lowercase a, but we have a macro that is called assert with an uppercase a. And the difference is that while it still takes this condition here, it produces an exception that carries information. So when assert finds that this condition is not satisfied, it produces an object of type, in this case, exception index range, which would say that I needs to be between 0 and size, where size is exclusive, 0 is inclusive, so it's a half-open range. And it would attach to this information, to this object, to this exception object, information about the file and line where this happened, and it would produce a stack trace on the console. So you can oftentimes find bugs in deal.II already by looking at the stack trace that's printed on the screen without even running it in the debugger. Because it takes time to run it in the debugger. It takes time for Eclipse to start it up and so on and so forth. It's a lot easier if you get to see on the screen right away where it happened, what the condition was that was violated, and so on and so forth. But by and large, the assert macro that we have does exactly the same thing as the standard C macro, with the exception of printing more information. So this is a precondition. Now, postconditions state something about what the return value or the state of an object after a call should be. So let's say, for example, you were to compute something like the norm of a vector. In that case, you know that the result must be a non-negative number, right? The norm of a vector cannot be -1. That would violate the definition of what a norm of a vector is. So this is something that you can verify at the very end of the function. That's why we call it a postcondition. And again, oftentimes postconditions are recorded as part of the documentation of a function. And every violation of a postcondition typically indicates a programming error. Not in the place where you call this function, but within this function, right? If the function computes the norm of a vector and it wants to return -13, then obviously this function cannot have been implemented correctly. So postconditions are things that test not the input argument, but that test the implementation of a function. So let me take this example of computing the norm of a vector and show you how you would implement this. So you would have, again, your vector class and all of the elements as before. You would have a function that returns a double that computes the norm, and it does it in the following way. So you start with a sum equals to 0. I'm talking about the L2 norm, of course. I loop over all of the elements of this object, and to the sum I add the square of each individual vector element. Okay. Now, from this I can compute the return value, and the return value would be the square root of the sum. And then I would have my postcondition, that's an assert, namely that the return value must be a number that's greater or equal than 0. And I can output a message. So the exception object in this case would not be exception index range, but exception message. And you could add some text here that would say postcondition about return value is violated. Something of this kind. So the point is that this is something that verifies the correctness of the implementation of this function. For example, if by accident we had not taken the product of this element with itself, but we just added up the elements. Let's say this is a genuine error that we make sometimes when we program. Let's say we just add the elements, then the sum might have been a negative number, and if we take the square root of this, we would get something that is not a number. Not a number is not greater or equal than 0. This comparison is going to fail. And so we're going to get in, the program is going to abort and is going to print an error message that the postcondition is not satisfied. So in this case, the addition of this postcondition has helped us to find a bug in this function. The third case that you could consider is something that is called internal conditions. So in the case that I just showed you, the computation of a norm is just a very simple algorithm, but oftentimes you have multiple steps in the algorithm. So for example, during mesh refinement, let's say you start on the coarsest level, and because we only want to have one hanging node per cell or per edge, if a cell that is adjacent to a hanging node wants to be refined, we also need to refine its coarser neighbor. Okay, so when we do this mesh refinement, we first need to refine all of those cells on the coarse level that have finer neighbors that will be refined as well. So there is an invariant that in this process, at every step, every cell should have at most one hanging node. And so what we do, let's say in big, well-written software, is that we have these internal conditions that at these places where we know that something needs to be true within the algorithm, that we add an assertion that verifies that this condition that we know to be true is in fact true. So this is what we call an internal condition. That's something that you would typically do in bigger functions that consist of multiple parts, or let's say a loop, where at the end of every loop some kind of invariant has to be true. So within this taxonomy of pre-post and internal conditions, one of the things you might argue that you can never get rid of preconditions. So for example, let's say we have debugged our code and it works and it only accesses elements of a vector that are valid. Then you could say, well, why don't you delete this assertion, this precondition in the access operator? Well, if we do this, then somebody else, or let's say maybe ourselves, we would continue to develop our code, and we would have to write an additional function that also accesses elements of this vector. If the assertion has disappeared, then we have no way anymore to make sure that in the place that we just edited or that we just wrote, we still access only valid elements, right? Because our codes keep growing. There is no way we can ever get rid of preconditions, because there will always be new uses of a function. And we could argue that of course, once we have written a function, we can get rid of the post and internal conditions, because once we have written the function, we have verified that it works, we know that these internal conditions are always true, and there is no need anymore to check them every time we call them. But it turns out that this is a bad idea, because in practice, you are never done with a function. Just because it runs now does not necessarily mean that 6 months from now you will not want to modify it somehow. So maybe, for example, you have this refinement algorithm, but you want to add an additional twist to it, that you want to, let's say, anisotropically refine your cells. So instead of refining every quadrilateral into 4, let's say you wanted to refine it into 2 only in x direction or only in y direction. Now, that means that you have to rewrite a lot of the code. The internal conditions that have to be satisfied at every step will still be the same. You still have to be able to say that at this point, this condition has to be true. If I had gotten rid of my internal conditions, I would be unable to verify that during the process of extending this function, everything is still correct. So the general rule is that you, and I can unambiguously state this from many years of programming experience, is that you should never get rid of assertions. That it's a bad idea to get rid of them, because you will at one point need them. As a matter of fact, it is certainly true that there will never be enough assertions. If you have something that can be checked, check it, because at one point or other, the condition that you have here will be violated, either because you introduce a bug or because somebody calls the function with an argument that you didn't expect or that was not valid. There can never be enough assertions. You will always benefit if you add more assertions in your code. It is a general truth. Okay, so of course there's a price to pay. So you have assertions, and that means that every time, for example, you want to access any element of the vector, you will have to run through this if statement that verifies that indeed I is less than n. And that makes your executable slow. It also makes them much larger than necessary. So typically, for example, in deal.II, when you run with all of these assertions in the code, your code will run approximately 4 to 10 times slower. So there's a definite price to be paid for this. The solution to this is that deal.II is built twice. So deal.II has these 8,000 assertions in there, and they make your code slow. But what we do is we build the deal.II libraries once with all the assertions in place. We call this the debug mode library. And if you go into the directory where you install deal.II, there is a file that is called libdeal_2.g.so. G refers to debug, because on the command line, when you ask the compiler to produce debug information, the flag is -g. And then we built a second version of this library that doesn't have this .g, where essentially we replace all of these asserts with nothing. And that means that when you call this function in the optimized version of the library, that you can access any element you want, and you will not get called out on it. So of course, the way we use these two libraries is that when you develop your program, you compile your program in debug mode with all of the assertions that you have in your own code. So, of course, it runs slowly, and but you will find all your bugs. So you compile it with the assertions in your code. You link against the debug mode library that has all of the assertions in deal.II, and whenever there's a problem, it will kick you out. Then, when the time comes where you want to do your production runs, let's say you do 2 more mesh refinements, the problem becomes 4 times as big, 16 times as big. Or you want to go from 2D to 3D, because you have already verified that all of the places in the code that you have run against the debug mode library, in all of these places you only access valid vector elements. Then you don't need them anymore, and you can run exactly the same code in optimized mode linked against the release mode library. And so this is the purpose of these 2 libraries. Of course, when you run it and you go back and you want to modify something, you change the boundary conditions, you change the mesh generation, you change the bilinear form. As soon as you start developing again, you need to switch back to debug mode. So optimized mode is really only you run the same executable that you have run in debug mode and it worked before, then you can run it in optimized mode or in release mode. So with this, I would like to ask you to try these sort of things out. I would like to show this to you here on this laptop. Unfortunately, the laptop that I used to demonstrate these things had a problem last night, as it always happens the night before you want to videotape these sort of things. The way this works is when you go to the tutorial directories. For example, you go to examples step 1, and you type the usual command cmake -d deal2 dir equals something dot. It prints a list of commands that you can say. So you can say, for example, make debug, and then it will build your executable in debug mode, and you can run it. Then you can say make release, and it's going to build the executable for step 1 linked against the release version of the deal.II library. And then you can run it again. And one of the things that you will find out is that it runs much faster, of course, than it does in debug mode. So play with these sort of things, but keep in mind that the general rule is always, when you develop, you always work in debug mode. Only when you're sure that the program works as expected, that's where you can switch to release mode and run it fast and run it on big computations.